Welcome to AI Frontiers, where we explore cutting-edge research in computer science and artificial intelligence. In today's episode, we'll be examining recent advances in cryptography and computer security from May 2025. As our digital landscape evolves, so do the threats and vulnerabilities challenging our information systems. The research we'll discuss represents the frontier of efforts to safeguard our increasingly complex digital ecosystem from sophisticated attacks while enabling secure communication and data protection. Join us as we synthesize the latest findings and innovations in this critical field. Before diving into specific research themes, let's establish the context of today's rapidly evolving digital security landscape. Cryptography and security research fundamentally aims to protect information systems from unauthorized access and malicious attacks. This field has become increasingly critical as organizations rely more heavily on digital infrastructure for their core operations. The stakes of security failures continue to rise, with major breaches potentially exposing sensitive data affecting millions of users or disrupting essential services. In recent years, artificial intelligence systems have introduced entirely new attack surfaces and security considerations that weren't relevant in traditional computing environments. Current research spans diverse areas including blockchain technology, differential privacy frameworks, adversarial attack mitigation, and secure authentication systems. Driving much of this innovation is the rising sophistication of adversaries, including nation-state actors, requiring researchers to continuously develop more robust security measures to stay ahead of emerging threats. The first major research theme emerging from our analysis focuses on privacy-preserving technologies. As data collection becomes increasingly pervasive across digital systems, researchers are developing sophisticated methods that enable useful analysis while protecting individual privacy. Differential privacy has emerged as a particularly important mathematical framework in this area, providing formal guarantees about the privacy of individuals whose data is used in computations. Chen and colleagues have made significant progress with improved algorithms specifically designed for privacy-preserving language model alignment. Their work addresses the critical challenge of how to train language models on user data without compromising privacy, which is particularly important as these models increasingly rely on potentially sensitive user interactions for improvement. In a different application domain, Westrich proposed hybrid approaches for smart meter data analytics that combine multiple privacy-preserving techniques. This research successfully balances the utility of fine-grained energy consumption data for grid optimization with strict regulatory requirements around privacy. The work addresses the fundamental tension between extracting valuable insights from detailed monitoring of household activities while ensuring robust privacy protections for consumers. Our second research theme examines hardware security innovations and blockchain technology advancements. Tashdid and colleagues introduced SafeSIP, a groundbreaking secure authentication framework for system and package designs. This framework leverages multi-party computation to enable zero-trust authentication in chiplet integration scenarios, addressing a critical vulnerability in modern semiconductor manufacturing where components from multiple vendors are assembled after fabrication. In the blockchain domain, Huang and colleagues conducted a comprehensive comparative analysis of blockchain architectures across major platforms including Bitcoin, Ethereum, and Hyperledger Fabric. Their research helps organizations understand the strengths and limitations of different blockchain implementations for specific use cases. Complementing this work, Singh provided a thorough review of blockchain's evolution beyond cryptocurrencies, highlighting ongoing challenges in scalability, interoperability, and governance as these systems mature. For resource-constrained environments, Vaha and colleagues proposed SEPAR, a lightweight encryption algorithm specifically designed for Internet of Things devices, balancing security requirements with the limited computational capabilities of these increasingly ubiquitous devices. The third significant research theme centers on adversarial attacks and content authentication mechanisms. Yuan and colleagues revealed concerning vulnerabilities in deepfake detection systems, demonstrating how these detectors can be compromised through sophisticated data poisoning attacks. Their research showed that once third-party data providers insert corrupted data maliciously, deepfake detectors trained on these datasets contain backdoors that cause abnormal behavior when presented with samples containing specific triggers. This finding undermines the trustworthiness of systems increasingly relied upon to authenticate digital content. In retail environments, Na and colleagues demonstrated how adversarial patch attacks can effectively disrupt object detection models, highlighting vulnerabilities in fully automated stores. As AI-generated content becomes more sophisticated, Sewer and colleagues analyzed optimal watermarking strategies for large language models, identifying methods for embedding detectable signals with minimal impact on text quality. Their work provides a theoretical foundation for distinguishing AI-generated content from human-written text. In related work, Bauer and colleagues developed inference attacks for speaker anonymization systems, proposing novel methods that outperform existing approaches for de-anonymizing speakers. Finally, Ammon and colleagues outlined a comprehensive security framework specifically designed for retrieval-augmented generation systems, addressing the unique vulnerabilities that arise when language models access external knowledge sources. The fourth research theme focuses specifically on AI system security, reflecting the growing importance of securing artificial intelligence infrastructure. Wu and colleagues created LibVulnWatch, an innovative graph-based agentic assessment framework for evaluating the security of AI libraries. This system coordinates specialized agents to extract, verify, and quantify risk using evidence from trusted sources. When applied to widely used machine learning frameworks and large language model inference engines, LibVulnWatch uncovered numerous additional risks beyond what existing tools could detect, including critical remote code execution vulnerabilities. Kokonis and colleagues introduced ROSA, a breakthrough approach combining advanced fuzzing techniques with metamorphic test oracles capable of detecting runtime backdoor triggers. In extensive testing, ROSA successfully detected 17 different backdoors in just 90 minutes on average, all without requiring manual reverse engineering. This represents a significant advancement over previous approaches that required substantial human intervention. Both of these innovations reflect the growing focus on supply chain vulnerabilities in AI components, where compromised libraries or frameworks can introduce security risks across numerous downstream applications. As AI adoption accelerates across industries, these automated security assessment tools become increasingly critical for maintaining the integrity of complex AI ecosystems. Several groundbreaking research findings stand out for their potential impact on the field. The SafeSIP framework developed by Tashdid and colleagues achieved secure authentication for chiplet-based systems with remarkably minimal overhead. Just 3.05% area increase while maintaining a computational complexity of 2 to the power of 192. This efficiency makes it highly practical for industry adoption. Wu and colleagues' LibVulnWatch system demonstrated extraordinary effectiveness, finding up to 19 additional security risks per library beyond what existing tools could detect when evaluating popular AI libraries. This included critical vulnerabilities that could potentially compromise entire AI systems. Yuan and colleagues' research exposed fundamental vulnerabilities in deepfake detection infrastructure, demonstrating how these systems can be compromised through data poisoning to create backdoors that allow malicious users to evade detection. The ROSA framework from Kokonis and colleagues represents a significant advancement in backdoor detection, finding all 17 authentic or synthetic backdoors from their benchmark in just 90 minutes without requiring manual reverse engineering. Finally, Sewer and colleagues established a mathematical foundation for optimizing language model watermarking, providing closed-form expressions for the fundamental trade-off between watermark detection power and text quality distortion. Researchers in cryptography and security employ several common methodologies to address complex security challenges. Differential privacy appears in multiple studies as a mathematical framework providing formal guarantees about individual privacy while enabling useful data analysis. This approach offers quantifiable privacy protection and allows researchers to make explicit trade-offs between privacy and utility through adjustable parameters. However, it typically introduces noise that can reduce accuracy, especially with small datasets. Multi-party computation enables multiple parties to jointly compute functions while keeping inputs private, supporting zero-trust computing where no single party needs access to all data. While powerful, MPC often involves significant computational overhead and communication complexity. Adversarial testing and fuzzing represent proactive approaches where researchers actively attempt to break security measures to identify vulnerabilities before malicious actors discover them. These methods effectively uncover non-obvious vulnerabilities but may not achieve comprehensive coverage of all possible attack vectors. More recently, graph-based agent systems coordinate specialized agents for complex security assessments, offering modularity and transparency but requiring careful design of agent coordination mechanisms. Traditional cryptographic techniques including encryption, hashing, and digital signatures continue to provide the foundational building blocks for many security solutions, though implementation details remain critical to their effectiveness. Let's examine one standout paper in greater depth. SafeSIP. Secure Authentication Framework for System-in-Package Using Multi-Party Computation, by Tashdid and colleagues addresses a critical security vulnerability in chiplet-based heterogeneous integration. This emerging paradigm in semiconductor manufacturing involves assembling components from multiple vendors after fabrication, creating significant security challenges. In traditional approaches, chiplet vendors must share their authentication signatures with the system-in-package integrator, creating a potential security vulnerability if the integrator is compromised or malicious. SafeSIP introduces a novel use of multi-party computation that enables zero-trust authentication without requiring a trusted integrator. The framework prevents signature exposure while maintaining security guarantees, effectively eliminating a major attack vector in modern semiconductor manufacturing. What makes this research particularly impressive is its practical efficiency. Achieving these security improvements with only a 3.05% area increase while maintaining strong computational complexity guarantees. This minimal overhead makes the approach highly viable for industry adoption, potentially transforming security practices across the semiconductor industry. The paper was selected for detailed examination due to its combination of theoretical innovation and practical impact on hardware security in an increasingly modular computing landscape. Our second featured paper, libVulnWatch, a graph-based agentic assessment framework for AI library security, by Wu and colleagues, introduces a groundbreaking approach to evaluating security in AI software components. As organizations increasingly rely on open-source libraries for AI development, understanding the security implications of these dependencies becomes critical. libVulnWatch coordinates a directed acyclic graph of specialized security assessment agents, each responsible for specific tasks in a comprehensive evaluation workflow. When applied to 20 widely used libraries, including popular machine learning frameworks and large language model inference engines, the system uncovered up to 19 additional risks per library beyond what existing tools could detect. These included critical remote code execution vulnerabilities and undocumented telemetry that could potentially leak sensitive information. What distinguishes this research is its ability to translate high-level governance principles into practical, verifiable security metrics. The graph-based architecture provides transparency and reproducibility, allowing organizations to understand precisely how security assessments are conducted. This paper was selected for its contribution to addressing the emerging challenges in AI ecosystem security, where traditional security tools often failed to capture the unique vulnerabilities introduced by complex AI systems and their dependencies. The third paper we're highlighting, Where the Devil Hides. Deepfake detectors can no longer be trusted, by Yuan and colleagues, reveals alarming vulnerabilities in systems designed to identify AI-generated media. As deepfake technology becomes more sophisticated, organizations increasingly rely on automated detection systems to authenticate digital content. This research demonstrates that these detectors are vulnerable to data poisoning attacks, where corrupted data inserted by third-party providers creates backdoors in the trained models. The researchers developed a trigger generator capable of creating passcode-controlled and even invisible triggers that cause deepfake detectors to misclassify content when specific patterns are present. This means malicious users could distribute or sell these triggers, allowing others to manipulate detector performance and escape accountability. What makes this research particularly concerning is that it undermines a critical line of defense against misinformation. As society increasingly relies on automated systems to distinguish between authentic and synthetic media, these vulnerabilities could have far-reaching implications for digital trust. The paper was selected for detailed examination because it exposes a fundamental weakness in our content verification infrastructure at a time when distinguishing authentic from synthetic content has never been more important. Looking toward the future, several clear research directions are emerging in cryptography and computer security. Post-quantum cryptography continues to gain urgency as quantum computing advances threaten to break widely used encryption algorithms. Researchers are developing new cryptographic primitives that can withstand attacks from quantum computers while remaining efficient enough for practical deployment. Automated security assessment tools for complex AI supply chains represent another growth area, as organizations struggle to understand the security implications of their increasingly complex technology stacks. Privacy-preserving techniques that balance utility, compliance, and protection in sensitive domains will become increasingly important as regulatory requirements around data privacy continue to evolve globally. As AI-generated media becomes more sophisticated and widespread, robust content authentication mechanisms will be essential for maintaining trust in digital information. These systems will need to evolve beyond current approaches that this research has shown to be vulnerable to manipulation. Finally, zero-trust security frameworks for modular hardware and software architectures will become increasingly important as computing systems become more distributed and component-based, with security boundaries existing within rather than just around systems. A brief note on our methodology. This synthesis was created using several AI tools including GPT Anthropic, Claude 3-7 Sonnet 20250219, for content analysis and generation. The text-to-speech synthesis you're hearing was performed using Deepgram technology, which provides natural-sounding narration optimized for technical content. Visual elements accompanying this podcast were generated using Google's advanced image generation capabilities. While we leverage these AI tools to process and present research efficiently, all content underwent careful review by human experts in the field of cryptography and computer security to ensure accuracy and relevance. Despite our thorough review process, we acknowledge that some oversights may exist in this synthesis. We continuously refine our methodology to provide the most accurate and comprehensive research overviews possible. Thank you for joining us for this exploration of recent advances in cryptography and computer security. To stay updated on cutting-edge research in this rapidly evolving field, subscribe to our channel for weekly research syntheses covering the latest developments. We invite you to join our community of researchers and technology enthusiasts engaging with these important topics. If you have suggestions for research areas you'd like us to cover in future episodes, please comment below. Share this podcast with colleagues interested in security research to help spread awareness of these critical developments. For additional resources and full references to all papers discussed today, visit ifrontiers.com. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from arXiv preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer. This video uses arXiv.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv.org.